So we have seen Word2Vec at multiple places. If you recall, in the Amazon Find Food Reviews dataset, for the Amazon Find Food Reviews dataset, when we learned various ways of featureizing text data, we looked at bag of words, TF, IDF, etc. But we also looked at Word2Vec. So when we discussed this, I just gave you an intuitive understanding of what Word2Vec is. Basically, Word2Vec, given a word, let's assume you give it a word, right? If you give it a word, it returns you a vector. It returns you a vector such that these vectors have semantically similar for similar words, right? So we saw, if you've forgotten what Word2Vec is, please go back and revisit this chapter called Amazon Find Food Reviews, where we discussed how Word2Vec works with a lot of nice examples, right? In this section, we'll understand how Word2Vecs are constructed, because in this earlier we didn't know how it is built. We just said, okay, it's a function in so we use the library gensim, where we give it a word and it would return as a vector, but we didn't know what is happening inside, and we'll try to understand that given our current understanding of a lot of deep learning right now, right? By the way, Word2Vec is not a deep learning algorithm, right? It's actually a simple neural network structure, very, very simple. And it was created by a team, by Mikolov and others at Google. I think this paper, if I'm not wrong, is around 2012. Actually, I don't recall the exact date. Let me quickly search for it, right? Word2Vec Mikolov, right? If you see the distributed representations, etc. Okay, this is a NIPS paper. Let's see which year it is. I think this is okay, Thomas Mikolov, etc. I think, I don't remember the date. I think it's around 2012ish. Okay, just let's look at Wikipedia, otherwise my favorite source of information. So if you just go to Word2Vec on Wikipedia, it says, okay, Word2Vec by Thomas Mikolov, blah blah blah. Okay, simple stuff. Okay, there will be some research paper here for sure. I think this is around 2012, 2013ish. Okay, see, the first paper is around, this is it, efficient representation. This is around 2013, right? So that's what I recall, around 2012, 2013ish paper. Very interesting research paper explaining Word2Vec and a couple of variations. But before we go to Word2Vec, let's understand a couple of very simple concepts. So let's assume I have a sentence like this: the cat sat on the wall. Okay, let's assume I have a sentence like this. Okay, so let me define a couple of things. Let's say I take this word. You can take any word and call it a focus word. Okay, let's assume I call sat as my focus word. Then all the words which are around it, which are around this word, are called context words. Right? You can say this is let's say a word. Okay, this is your focus word. Let's call a focus word as f. F here doesn't mean a function, it means a focus word. This is context word 1, context word 2, context word 3, context word 4, context word 5. So context words are words which are surrounding a focus word, right? Similarly, if I take cat as my focus word, the, sat, on the wall become my context words. Okay, we will use this concept, we'll use these definitions of what a context word is and what a focus word is to actually build the Word2Vec structure, right? The core idea here is that context words are very useful, right? Context words are very useful in understanding focus words, and vice versa, right? That's the core idea here. The core idea here is that if you know the context in which a word is used, okay, you can say a lot of things about the word itself, and vice versa. If you know the focus word, you can predict or you can understand what the context could have been, right? So that's the core idea here. We will use this concept of focus word and context word to build word vectors. There are two Word2Vec algorithms. One of them is called CBOW. The other is called skipgram. I'll explain both of them in this video. CBOW stands for continuous bag of words. CBOW stands for continuous bag of words, right? Even the name is slightly complicated. It's actually a very, very simple system. Okay, so we'll first understand CBOW and then we'll go to skipgram. These are two algorithms. These are two methods or two algorithms to achieve Word2Vec structure. Okay, there are two ways of getting word vectors. One of them is CBOW, the other is skipgram. Okay, so let's take CBOW first and understand CBOW. They're very, very related stuff. CBOW and skipgram are very, very related architectures. Okay, first let's start with CBOW. Let's assume I have a bunch of words, right? Let's assume my whole dictionary or vocabulary of words. Suppose let's assume I have a dictionary or vocabulary of words. Of course, tens of thousands of words probably, right? So let's say my length, so let's call my vocabulary as capital V. Okay, and let's say small v is the length of my vocabulary, is the length or size of my vocabulary. So V now represents the number of words that I have in my dictionary or vocabulary. Okay, let's start with that. Okay, so first step. The second step is that let's assume I use one-hot encoding. Let's assume I use one-hot encoding to represent each word, which means given any word Wi, I can represent it as a V-dimensional vector, binary vector, right? So this is basically a binary vector of V dimensions, right? Because I have a total of V words in my vocabulary. So given any word in this vocabulary, I can always represent it as a V-dimensional, not real valued vector, but a binary vector, right? So let's start with this. Now let's draw the architecture first. So let's assume I have, okay, first let me draw it and I'll explain this. So let's assume each of these boxes, okay, let's assume each of these boxes is a V-dimensional one-hot encoded word. Okay, this is a V-dimensional. So think of this as the input layer in your system. Okay, think of this as the input layer in your system. Each of these is a V-dimensional vector. Okay, this is your input. And the first input is the context word C1. Look at this example. I take C1, which is the word on. I'll represent on as a one-hot encoding. Okay, and I'll put it here. So this is a binary vector representing on. This is for context word 2, context word 3, so on and so forth, context word K. Okay, so I have K context words. So in CBOW, what we try to do is this, the core idea of CBOW is this. Given context words, can we predict the focus word? Right? Because we agreed that there is a lot of information about a focus word that is present in the context words, right? So the core idea of CBOW is, given context words, let us try to predict the focus word out of this. Okay, so my input is context words. What will be my output? My output will be the focus word. Okay, so let's assume all of these are connected to an n-dimensional hidden layer. Let's say this is an n-dimensional hidden layer. Let's assume this is an n-dimensional hidden layer. And this hidden layer has linear activations, not sigmoidal activation. And what is linear activation? Linear activation is if you input Z to it, it outputs Z, where Z is W transpose X. So whatever is the weighted sum that you get of your inputs, you just simply output that. Okay, so this is fully connected to this. There are n dimensions here, right? There are n units here. Okay, n dimensions. So this is fully connected. This is also fully connected. This is fully connected, so on and so forth. Fully connected. Now let's see how many weights are here. If you think about it, how many weights are here? There are V values here and there are n values here. Okay, there are V values here and there are N values here. So total of V cross N. So this weights, there are V cross N weights. Let's call these weights as W superscript 1, V cross N. So W1 is all the weights that go from my first context word to my hidden layer. So this is W2, this is again V cross N. Okay, so N here is the dimensionality of the hidden layer. So V typically is the, so remember what is V? V is the dimensionality or the size of the vocabulary. V is very large, V is like some tens of thousands. Okay, N now, so this is an n-dimensional hidden layer. This is my input layer. Okay, this is my hidden layer. Sorry, let me change it. So this is my hidden layer, this is my input layer, and now let's see what is my output layer. Okay, so we have seen input and this. So my output layer, see what do I want to predict, right? I want to predict the focus word. I want to predict the focus word, which is a vector of size V dimensions. Okay, and I can predict any of the V words, which means what I need here in my final layer. In my final layer, what I need here in my output layer. So this is my output layer. What do I have to predict? What is my output? Okay, from this basically I get my output. My output here needs to be, my output that I get here needs to be a V dimensional binary vector, ideally. Okay, because I'm trying to predict the focus word, and the focus word is represented as a binary with one hot encoding. The focus word is also represented as a V dimensional binary vector, right? So the activation unit that I use here in my is basically not sigmoid, sorry, it's basically my softmax. Because what can softmax do? Softmax, okay, this is again fully connected. My softmax layer, right? We've discussed softmax, right? Softmax is a generalization of logistic regression for a K-class setting. Here our output is a V class because only one word. So from the output, only one of them is set to 1, rest all of them are set to 0. So you can think of this problem of predicting a focus word. So predicting a focus word, you can think of it as a multi-class classification. You can think of it as a multi-class classification problem, isn't it? Because you're trying to predict one word out of a repository or a collection of V words. So the output word can belong to any one of the V words, right? So this is your architecture. And how many weights are here? See, there are, okay, let's look at this. So you have a softmax here, right? You have a softmax layer here. Softmax layer has how many activation units here, right? You have V activation units because you have to generate a V dimensional output. Okay, and this connectivity here, let's call it just W N cross V, because you have N units here and you have V units here, because you need a softmax of V units. Okay, you need a softmax of V units to generate a V dimensional output. This is the structure of CBOW. Very, very simple. So you have only input layer, you have a hidden layer, and you have an output layer. Okay, and this is the structure. Just look at the number of weights. So the way it works is, first, let's assume you have your huge repository of text. The way you train a CBOW, is this. You take your whole text repository. You take all of your text, maybe take all of Amazon food reviews text. Take all of Amazon reviews text, right? Take all of this text. Now create these combinations of focus word and context words. Okay, you can create lots of, see, this is just free-flowing text, right? So just from one sentence, take a sentence like this. I can say my focus word is sat and my context words are the cat on the wall. This is one example. If my focus word is cat, my context words are the sat on the wall. So I can create lots of these combinations of focus words and context words, right? So this becomes my training data. So given text repository, given a repository of text, I create a data set. Of focus words and context words. I create this data set and I train this neural network, my CBOW neural network. Okay, this is a very, very simple neural network if you think about it, right? I can train this neural network using this data set. And at the end of the training, what do I have? I have all of these weights. See, at the end of training, at the end of my training, at the end of the training stage, I have all of these weights and I have all of these weights, right? Now, if you look at these weights, okay, these weights, let's take this W. This W is an N cross V. So given any word, so if you look at this matrix, let's just look at this matrix, right? This matrix is an N cross V matrix, which means it has N rows and V columns, right? It has V columns, column 1, column 2, so on and so forth, column V, and it has N rows. Now, given any word, remember our vocabulary is of size V. So given any word Wi, there is going to be a column corresponding to it in this matrix. Again, this matrix is this matrix. So I'll just write it down clearly here. So I take this matrix that I have here. Because all of the information in the context words, has been summarized in this smaller matrix. So given any word I, if I take this vector is an n-dimensional vector. This vector, so let's call this as vector I. This vector I now, so for every word Wi, there is a vector I in this matrix. This vector I is an n-dimensional vector, right? So in Word2Vec representation, remember in Word2Vec representation, given a word, you want to give a vector representation to it. So I can use this matrix, as my representation. So this matrix alone, this matrix that I have, this Wn cross V matrix, right, of size N rows and V columns. So given any word Wi, there is going to be a corresponding column in this, and I'll use this vector that I get. So whenever I say Word2Vec of Wi, what I return is vec I, which belongs to an n dimensions, right? So if you want a 200 dimensional Word2Vec, what you do is you set your vocabulary size is dependent on the data set you're given, right? You just set n equals to 200. You just set this n equals to 200 and you get a 200 dimensional representation at the end of your training, because you're just using this matrix of weights. This matrix of weights are connecting the hidden layer and the output layer, right? So this is CBOW, very, very simple algorithm, right? So in the next section, we will see in the next video, because we have seen CBOW, right? Very, very simple algorithm. We will see skipgram. Skipgram is very, very similar to CBOW, but with small subtle changes. We'll understand that in the next video.